All right, so in the last video, we defined what a vector valued function was, and we took some derivatives. We found a position vector, differentiate to get a velocity, differentiate again to get an acceleration, and we talked about speed being the magnitude of the velocity vector. So we're going to talk about anti-differentiating vector valued functions today and what we can use those for. All right, so if I define a vector valued function r of t to be x of t, y of t, then the antiderivative of the vector r is the integral of the x component with respect to time and the integral with the y component with respect to time. Now, where we use this most often is if we have a velocity vector and we want to go back to position. So if I integrate the components of my velocity vector across a time period, I will get a displacement in the x direction and a displacement in the y direction. That will give me an overall displacement vector. So what does that mean in two-dimensional motion? So if I have a particle sitting right here, and then I work out that it has a velocity vector of this, a displacement vector that looks like this, then I'll know that its final position will be right there. So this is displacement in vector form, displacement in both the x and the y direction. So particle moves in a plane with a velocity given here. When t is equal to 0, the particle is at the point 2,5. Find the position of the particle when t is equal to 3 and the total distance traveled. All right, so what we're going to do here to get a position. So we know that we start at the point 2,5. So here's the point 2,5. 2,5. 2,5. Now, in order to figure out where I end up, what I'm going to need to find is the displacement vector. Because once I determine what the displacement vector is, we'll call this the displacement vector, then I'll be able to figure out where I ended up. What is my position at time 3? So the way we're going to do that is we're going to integrate each of the components to get the displacement vector. So the displacement vector is going to be found by integrating the x component across the time interval starting at 0 and going to 3, and integrating the y component starting at 0 and going to 3. So, maybe it's easiest to do this off to the side here. So what's the integral of 5t squared with respect to t from 0 to 3? Antiderivative is 5t cubed over 3 on the interval from 0 to 3. So that is 5 times 3 cubed over 3, which is 5 times 9, or 45. And then the integral from 0 to 3 of t dt is t squared over 2 from 0 up to 3, which is 9 halves. So my displacement vector is 45, 9 halves. All right. The displacement vector tells me how the particle changes over the time period. So the idea is always is that if you take your, in one-dimensional motion, it applies to 2 as well, take your initial position, add your displacement, that gives you your final position. So my initial position was 2, 5. My displacement is 45, 9 halves. Summing those together, we end up with 47. 9 halves is 4.5. So plus 5 is 9.5. So what's that? 9.5 is 19 halves? 19 halves, right? Yeah. So 47, 19 halves is the final position. So that means I ended up here at the point 47, 19 halves. All right. So the position at time 3 is therefore, I'm going to find a place to write it here. Position, I'm going to do it this way. We'll use the R notation. r at 3 is therefore 4719 over 2. And then to find the total distance traveled is length. So recall that in previous notes, we had an equation for finding the length of a curve. The length of the curve is given by integrating dx dt squared plus dy dt squared square root integral with respect to t. It's effectively integrating the speed as a function. So in this case, that is 5t, that's 25t to the fourth, that's dx dt squared, plus t squared square root integral from 0 to 3 with respect to t. And again, I'm sorry, I wrote so big over here. I don't know if we can simplify this. Let's see. I can factor out a t squared. 25t squared plus 1. Yeah, it looks like this is not one we're going to be able to do. So let's just do this one on the calculator. So I'm going to do this one on a calculator. So it's going to look like this. Math. And generally, they would allow you to use a calculator on these, only in rare circumstances where it's really easy. And this one just didn't come out easy. Square root of 25x to the fourth plus x squared dx. All right, let's see what we get. We end up with 45.286 as the total distance traveled. So just to be clear, displacement is the direct path to how you get there. Your total distance traveled would be the actual length you move to get there, which is not necessarily in a straight line, depending on how you're moving.